346 through 353. The Chapter 6 wrap-up is on page 357. For practice, complete Exploration 6.3. In Section 6.3, we'll look at the theoretical approach for comparing two means, both the hypothesis test and for confidence intervals. Once again, the central limit theorem is going to help us out. Under the central limit theorem, with certain validity conditions met, the sampling distribution of the difference in sample means, x bar 1 minus x bar 2, will be approximately normal, centered at the difference in true means, mu 1 minus mu 2, with standard deviation the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Notice this distribution relies on the true means for population 1 and 2 and the true standard deviations for population 1 and 2. We do not hypothesize about sigma 1 or sigma 2, so we will be back to using the t-distribution. As always in a hypothesis test, we will assume the null hypothesis is true, or that mu 1 is equal to mu 2 in this situation. With that assumption in hand, we can simplify the distribution from the previous slide to saying that the difference in sample means under the null hypothesis will be normally distributed, centered at 0, with standard deviation root sigma 1 squared over n1 plus sigma 2 squared over n2. So this tells us that the center of the null distribution will be at 0, but we still don't know sigma 1 or sigma 2. Any ideas on what we should use instead? Let's use the sample standard deviations of each group as an estimate of the population standard deviation. So S1 and S2 will replace sigma 1 and sigma 2, and our formula for the standard error of the difference in means will be S1 squared over n1 plus S2 squared over n2. As with the standard error formula for a difference in proportions, students often get this calculation wrong if they try to do too many steps in their calculator at once. I would recommend in your calculator doing S1 squared over n1, then S2 squared over n2. Add those two answers, then take the square root at the end. Finally, this gives us our theoretical test statistic, or standardized statistic, of t is equal to x bar 1 minus x bar 2, our observed result, minus 0, our null value, divided by that standard error formula that we just walked through. Theoretical interval, we no longer need to assume that mu 1 is equal to mu 2. But since that had no impact on our standard error, we're using that same formula of the standard error of the difference in sample means is equal to the square root of S1 squared over n1 plus S2 squared over n2. Be careful, your book made a few errors in writing this formula. The one presented here is the one you want to use. That gives us a confidence interval of our observed statistic, x bar 1 minus x bar 2, plus or minus a multiplier times our standard error of x bar 1 minus x bar 2. Remember, the multiplier depends on the confidence level, and since it's coming from the t-distribution now, we will always tell you what multiplier to use. Again, be sure when interpreting confidence intervals to include the order of subtraction, either by explicitly including it in the interpretation or stating that one group is higher than the other. Recall in Section 2.2 and 3.3, the validity condition required the data to be either symmetric or for the sample size to be at least 20 and not heavily skewed. Well, now we have two groups, so the validity condition must hold in each group. That is, both groups need to be checked for either symmetric data or a sample size of at least 20 and not heavy skew.